Welcome to week 5. So this week we're going to be looking at matrices and linear algebra, which gives us a way of tackling some of the things that we've seen in the last couple of weeks. Things like systems of linear equations and also systems of differential equations. So just to remind you, one of the examples that we looked at last week was balancing a chemical equation. And we saw, if we kind of figured out what it was that we were trying to do, that really we were trying to solve a system of linear equations. And when we used Gauss reduction, which was kind of a mission, we ended up with this solution here, which basically told us, for example, the ratio in which we would need to put the reactants in order to get various products without any waste. Similarly, we could use those equations if we knew how much of a particular product we wanted to figure out how much of each reactant we would need to include. But you're probably thinking, well, that wasn't super useful because I could have just done that by substitution or something. So I need to tell you that I promise that matrices aren't only for torturing you. They really are very useful. And even though you might be wondering when you would ever use Gauss reduction, I'm going to give you a few examples of places where essentially it's Gauss reduction that solves the problem. So if you're interested in chemistry, and particularly in quantum chemistry, then it turns out you're going to have to learn a little bit of quantum mechanics. And in quantum mechanics, things like position of a particle are almost entirely described using matrices. And when particles interact and you have things happening, you're going to need to use matrix algebra, linear algebra, in order to solve the problem. On the other hand, if perhaps you're interested more in ecology and you're thinking about populations and how they change over time, a very, very common model that gets used in many different situations is called an age-structured model. So here we have a situation where we're thinking of a population of organisms which only breed, for example, once a year. So we have within the entire population a kind of a stratification by the year in which each individual was born. And we can look at how overall the population changes. So if we draw a diagram, you'll see that if an individual starts in population 1, then a year later it will go into the second year category, it'll go into year 3, and so on. And also we can think about, okay, we're going to have various of the organisms in the different years who will be breeding, and they always contribute to the first year category. So we have these arrows here which indicate that organisms in our second year category are contributing some amount to the first years. Similarly, our 3-year-olds are also contributing, and so on and so on. And one of the things you might want to know is, if you have a population like this, how is it going to evolve? So we have looked a little bit at evolution of populations, for example, with our dynamics of the hare and the lynx. But this is a different situation where we're actually going to end up needing a matrix. And the key matrix that you would work with looks like this. And this gives you a way of saying, and we'll see this a little bit later how to do this, if I multiply this by the number of individuals in each category, so in each of our year categories, multiplying my matrix by that vector of populations is going to tell me what the new population stratification would look like. And that, if you bear in mind that you might have 10 or 12 or even more different years of populations, being able to do a single calculation like that is pretty cool. So something that I've just been learning about that I didn't know that matrices were used for is genome scale models, which are mathematical representations of reconstructions of metabolic networks. So basically what we've got is a situation where we look at the genome of whatever organism we're particularly interested in, and from there people, not me, are able to construct what the metabolic network of a particular set of reactions might look like. So we're thinking, for example, glycolysis, metabolism, or something like that. And there's a whole complicated, you've got different chemicals and they're all reacting indifferently, and there might be different pathways. And if you want to figure out kind of overall how this whole network works, it turns out that the trick is going to be to use a matrix called the S matrix, which really tells you how various metabolites and the reactions link together and how they interact. And then you can put together equations and you can solve for how the metabolism of this particular network that you're interested in works. So I thought that was pretty interesting. Okay, so hopefully that gives you a little bit of hope that Gauss reduction and working with matrices is not just a monumental waste of time. It's pretty important. And the good news that I will tell you is that nowadays computers will do all your Gauss reduction for you. It's just you kind of need to know how Gauss reduction works so that you can kind of sanity check your computer's calculations, because, you know, computers do screw up sometimes. So all of that is to say that matrices are really important, and I would say in comparison with functions, they're almost as important when it comes to modeling as functions. And although we won't look at this in this course, you can actually have functions which take matrices as inputs, and you have some matrices whose entries are actually functions. So in fact, you can have functions and matrices all playing happily together. So nothing we do this semester is ever going to be lost. You can always put it together. All right, so let's just clarify what these matrix things are. So simply put, a matrix is a rectangular array of numbers. So for example, you could have 1, 2, 3, 4, 5, 6. That's a perfectly good matrix. And usually I will use these round brackets, but some textbooks will use things like a square bracket. Okay, so we've already seen an augmented matrix. Now that we're thinking particularly when we're just solving systems of linear equations, and this is a situation where we have our coefficients of our linear equation, and we have our line which represents our equals, and we have some numbers on the other side. So an augmented matrix is really one of these things that has this line here, and it's all about solving a linear system. But more generally, a matrix is just some rectangular array of numbers. So both of those are matrices, something like 1, 2, 5. That is not a matrix because it's not rectangular. There should be something here. Okay, so that's not a matrix. So now that we've got many different numbers happening in one matrix, we need some way of referring to the individual numbers in the matrix, and we call that each one of those a matrix entry. Sometimes, depending on the textbook, you'll hear it called a matrix coefficient. We also sometimes want to refer to a particular row or a column, and not being particularly inventive here, if you want to talk about a row, you talk about a row. So that's a horizontal line, for example. That's a row. And if you want to talk about a column, that's going to be a vertical line of entries. Okay. So if we have a look at these matrices over here, so our matrix A, it has 4 entries. It has 2 rows, 2 columns. Our matrix B, so notice here I have variables which are still representing numbers. So you can have, as I said, functions within matrices, because each of these is a function. And this has 2 rows and 3 columns. Now, we sometimes refer to matrices which have, for example, only 1 column or only 1 row as vectors. So these are matrices, but we also call them vectors. and you probably encountered vectors before if you did physics, which I know you did, we will refer to something like this as a column vector if we want to specify the fact that it has entries that go down, and over here we have a little row vector here. And the other thing to notice in the notation here, when I'm talking about matrices and I want to name a particular matrix, I will usually, and most mathematicians will use a capital letter to represent that matrix. So we have A, we have B, but when we're talking about vectors, the notation might change a little bit if you're specifically thinking about it as a vector rather than just a matrix. So you'll use a lowercase letter and boldface, or you might use lowercase with a little arrow on top to tell people that this is a vector that you're dealing with. So if you see something with a capital, it's probably a matrix. Something with a boldface lower letter or a lower letter with an arrow means we're specifically thinking about it as a vector. And I'm not going to talk a lot about vectors as vectors in this course, but there's the whole aspect of physics and vectors where the mathematics of that is specific to being a vector rather than just a matrix. Other things, now suppose I want to refer to some of the entries in my matrix A. Well, then I will usually refer to a particular entry using a lowercase of the uppercase name of the matrix. So for example, A, and then the indices of the row and column in which that particular entry is found. So for example, this entry 1 is found in the first row and the first column. So A11, the entry A11, is equal to 1. On the other hand, if I want to refer to this entry over here, it would be A first row, second column, and it's equal to 4. So this gives us a way of kind of pulling out individual entries from our matrix. So obviously we have a situation where our matrices can be any size, so we want to be able to talk about the size. And we're going to need two numbers to describe that. We need to know how many columns and how many rows. And simply by convention, we always list the number of rows first. So for example, this matrix here, matrix D, the size of D, which I can indicate using absolute values, the size of D is going to be 2 rows is 2 by 3 columns. And usually we'll say a matrix is m by n, where m is the number of rows and n is the number of columns. So that was why when I was talking about entries in our matrix A, I always first gave the row and then I gave the column. And again over here, row first, then column. Obviously, if you're talking about a square matrix, so a matrix that has the same number of rows and columns, then the two numbers are the same. And so often if we're talking about a square matrix, we'll just say that it has size n to mean that it has size n by n. So if someone says the matrix has size n, you know that you're dealing with a square matrix, a matrix with the same number of rows and columns. All right, so just to check, so the dimensions of this matrix A over here, that's going to be 2 by 2. Matrix B is going to be 2 rows by 3. Our vector V, our column vector V, has 3 rows and 1 column, whereas our vectors X has 1 row and 2 columns. All right, so the key thing about being a vector is that one of your size dimensions is 1. So what do I mean when I'm talking about matrix algebra? So I don't know if you know where the word algebra comes from, but it's actually derived from an Arabic word, Algebra. And this comes from a treatise that was written a long time ago in 1830 by a Persian mathematician, Muhammad ibn Musa al-Khwarizmi. And the title of the treatise, which I cannot pronounce, can be translated into the compendious book of calculation by completion and balancing, which really was just a long essay on how to solve linear and quadratic equations. So it was kind of the first actual algebra. So a couple of interesting things here. So here's where algebra comes from. But there's another word, so this gave us algebra. But in fact, our Persian mathematician also gave us the word for algorithm. So it was al-Khwarizmi, but that became algorithm. So he was pretty influential. So when you're thinking about algebra, what you're really thinking about is doing mathematical type computations like you would do in arithmetic, but with non-numerical objects. So when you're doing algebra, you're working with things like x's, which aren't numerical. And you can also do algebra with things like matrices. And if you were to carry on doing more maths, you'd find other kinds of objects that you could do algebra with, that gives you a different kind of algebra. So if we're studying matrices, we need to actually study the algebra of them. How do you work with them? So that's what we're going to look at next. So key to the idea of algebra is the idea of two things being equal, and how do you tell if two things are equal? So we are really used to doing this. I mean, you know how to solve things like y is equal to 6. That means that y is equal to 6. But how do we talk about equality if we've got things like matrices which have more than one entry? So then we have to have a couple of criteria, not just one. The first thing is our two matrices have to have the same dimensions. So they have to have the same size, same number of rows and same number of columns, in that order. So it's not enough to have a 2 by 3 matrix and a 3 by 2. They both have to be 2 by 3. And then the second thing is corresponding elements have to be identical. So take a moment and think about that, and then answer these questions. For what values of x is b equal to a, and c equal to a, and d equal to a? And think about how you would answer those. Have you done it? Okay, well, let's check. So I'm going to add a page. So let's ask for what values of x is b equal to a. All right, well, what does this say? We've got our a and our b. So the first thing we check is, are the dimensions the same? Because if the dimensions are not the same, then there'd be no values, because the whole thing is not equal. So our a is a 2 by 3, so that's looking good. And yes, our b is also a 2 by 3, so that's fine. Okay, so now we have to make sure that corresponding elements are identical. So for a to equal b, we need that our 1 is equal to x squared. Okay. Then the next thing we need is that our 1 is equal to 2x plus 3. So actually, let's use a different color for that. We need 1 is equal to 2x3. Sorry, 2x plus 3. And we keep going. Okay, so then we check the rest of our entries. And we've got 3 is equal to 3, so that's fine. Those two are the same. Our minus 1 is equal to -1, so that's fine. And again, our 3 is equal and our 2 is equal. Okay, so the only two entries that we need to make sure are equal are these two here. And we need these to be solved simultaneously because they have to be true at the same time. Okay, you'll be glad to know I'm not going to use Gauss reduction here. I'm going to solve one and then see if I can find a solution. So for our first one, 1 is equal to x squared. This tells us that x is equal to 1 or x is equal to -1. Okay, and then our equation here, which is 1 is equal to 2x plus 3, tells us that we need to have -2 is equal to 2x, which tells us that x is equal to -1. So if we look at these, solving these simultaneously, the only solution which is valid for both of them is x is equal to -1. So x is equal to -1 means that a is equal to b. Notice that if I put in x is equal to 1, then I would have that this term would be equal to 1. So that would be fine, but this term would be equal to 5, and it needs to be equal to 1, so that wouldn't work. Okay. So you can work through c equal to a and d equal to a in your own time and make sure that you're happy with that. I haven't actually solved this yet, so it might be that you can't find any values. They don't have to be equal. All right, I'll put the solutions in the final version. Okay, so now we have this notion of matrix equality, so we can start thinking about how we add matrices together, things like that. So matrix addition and subtraction act exactly like you would hope that they would. So I'm talking about addition first. Things that have to be true. We can only add two matrices that have the same size, because we're going to be adding corresponding entries. And if you don't have a corresponding entry, you can't add it, so it doesn't work. Okay, so if we have a look at this first example here, I've got this matrix here, which is 3 by 2, and this matrix, which is 3 by 2. So we can add them, and we have to add corresponding entries. Okay, so my first entry will be 1 plus 0. My second entry in the first row will be -2 plus 1. My third entry will be 3 plus 1. Fourth entry will be 4 minus 2. Then I'm going to have a -5 plus 11. And let's find another color. Maybe we can have yellow. We're going to have a 6 plus 0. Oh, that yellow is not great. So this is just me doing this in excruciating detail. You don't need to do this. You could go straight to the next step, which says the first element of the sum of those two matrices is going to be 1. First row, second column will be -1. Then we'll have a 4, we'll have a 2, we'll have a 6, and we'll have a 6. Okay, so this works exactly like you would expect. You just work element-wise. So you can check for yourself. You do exactly the same thing if you're talking about subtraction. So if we have, actually let's have a look at this. So we've got 1 minus 0, which is 1, -2 minus 1, which is -3, 3 minus 1, which is 2, 0 minus -2, so that's going to be 2, -4 minus 11 is going to be -15, and -5 minus -1 is -5 plus 1, so that's going to give us a -4. Okay, so addition and subtraction of matrices is very straightforward. Now, one of the things that you'll know from algebra is that 0 is quite an important number because you can add it or subtract it from any other number and it doesn't change the original number. And we want to have the same idea. It's going to be useful in matrix algebra as well. So we have the idea of a zero matrix, which unsurprisingly is a matrix where every entry is 0. And it's typically written like this, like a boldface 0, or sometimes if you're handwriting, so it's hard to do the boldface, you might also write this as 0 with an arrow on top. So it's the arrow kind of like a vector, but it's sort of saying, okay, I'm a matrix. So you might be saying, okay, but which matrix are we talking about? What are its dimensions? And it's kind of assumed that you know the dimensions that you're talking about, that it will be whatever the dimensions are necessary in order to solve the problem you're looking at. So for example, here is a 0 matrix. Here's another 0 matrix. And if it turns out that you are dealing with multiple 0 matrices with different dimensions, then you would usually just do something like this. 0, this would be 0, 3 by 2. And you just put the dimensions below. This is the 0, 2 by 2. Things like that. Okay. And if you go back to what we did with subtraction and addition, notice that if you take the appropriately sized 0 matrix and add it to any other matrix, you just get the original matrix. So for example, 1, 2, 3, 4, and we're going to add the 0 matrix of the right size is going to give us back the original matrix. So it behaves exactly like the matrices, the numbers that we're used to working with. It doesn't change anything. Okay, so now we really have two sets of things that we can work with. We have scalars, which are the individual numbers that we've been working with since we were like 3. And then now we have matrices, which are rectangular arrays. So we can also think about how do you combine those. And one way of doing this is to multiply a matrix by a scalar. So this gives us a way of scaling the original matrix. So for example, I could say something like 2 times 1, 2, 3, 4. And this really says just multiply every entry by 2. So this is going to give me 2, 4, 6, 8, and so on. Not much to it. Okay. All right, so we've done the basics of algebra. We've done addition and subtraction. We've talked about a 0 matrix. And now we need to talk about multiplication. And this is where matrices take quite a different route from normal multiplication with numbers that we're used to. So this might, if this is new, this might take a little bit of getting used to. But it turns out, even though it's going to look a bit weird, it's super useful. So the first thing that we're going to do is we're going to define the dot product of two vectors, which you might well have seen in physics. So the first thing to think about whenever you're thinking about multiplication of vectors or matrices is you need to be very aware of the dimensions. Not something you need to worry about with normal numbers, but with matrices and vectors, you need to think about the dimensions. So if we have a row vector and a column vector with the same number of entries, so they have the same length if you measure how many entries, then we define their product, their dot product, which we denote like this with this little dot sitting over here, as the sum of the product of their individual entries. So for example, do I have space here? Okay, let's do an example over here. So let me take a row vector. So I'm going to let my x is going to be equal to 1, 2, 3. And I'm going to let my column vector y be equal to 4, 5, 6. If I work out x dot y, then I need to take x11 times y1 in x1 times y1. So notice when we're talking about vectors, we don't need to use two indices to refer to the elements because we know either it's a row or a column. We know which it is. So x1, so that's going to be a 1 times 4 times 4. Now I'm going to have, plus 2 times 5 plus 3 times 6. Now I've written it like this to show you notation that might get confusing. Because the two things on either side of this dot over here are vectors, this means dot product. But when I'm working with numbers, so in each of these cases over here, again, I can use the dot, but now it's meaning something different. It's just meaning multiplication of numbers. In this case, real numbers, which are actually quite different operations, but the same notation gets used. Sorry about that. Okay, so let's finish this up. So we've got x dot y is going to be equal to 4 plus 10 plus 18, which is going to give us 32. So the thing to note here is that we start out with two vectors, an x and a y, but our dot product ends up giving us a scalar, a single value. So we have two vectors and our dot product ends up giving us something quite different. It's just giving us a number. And because this is a scalar, you will sometimes hear the dot product referred to as the scalar product, which basically says you take two vectors and you do the thing that gives you a scalar. And this is opposed to the cross product, which we're not going to talk about, but you might have seen in physics, where you take two vectors and you do a different kind of multiplication, and that gives you another vector. Okay, all right, so that's the first step, the dot product. And now we can use our dot product to define what it is to multiply two matrices. So there's a lot going on in this definition that you need to be quite aware of. So we're going to let matrix A have size n by n, and matrix B have size n by r. And the key thing to note here is that the number of columns of A must be equal to the number of rows of B. So you'll see straight away we can't just multiply any two matrices together. They have to have the right dimensions. And this is in contrast to normal multiplication of numbers, where you can just multiply any numbers that you like. Okay, so supposing you have an A and a B which have the appropriate dimensions, then our matrix C, which is A multiplied by B, is a matrix which has dimensions the same number of rows as A and the same number of columns as B, and how do we find its entries? Well, entry Cij, so the ith row and jth column, that particular entry is what you get if you take the dot product of row I of A and column j of B. Okay, sounds weird. Let's just look at some examples. Okay, so the first thing to do when you're doing matrix multiplication is check that you can do it. Do your matrices have the right dimensions? If you can, figure out the dimensions of the new matrix that you're going to get. So let's have a look. So this matrix over here has 2 rows and 3 columns, and our next matrix has 3 rows and 2 columns. And the key thing is that we can only do multiplication if those two things are equal, so we're good to go. So we can do multiplication, and the next thing that we know, so let me just make a note here. The next thing is that we look at the number of rows of the first and columns of the second, and that tells us that our answer will be a 2 by 2 matrix. Okay, so the way I tend to work this is I will kind of sketch what my new matrix is going to look like, and I put little dots to tell me where I need to have entries. So I know that I've got to find 4 entries. All right, so let's work out this first entry over here. So that is our entry which says take the first row of our first matrix and dot it with the first column of our second matrix. Okay, and then if we look at this entry over here, that is the 1, 2 entry, so it says take the first row and dot it with the second column. So that's going to be our 1, 2, 3 dotted with 2, 4, 6. Okay, let's look at the next one. So now I'm thinking about this entry over here. So that's in the second row and the first column. So I'm taking the second row, which is 4, 5, 6, and I'm going to dot it with the first column. So that's going to be 1, 3, 5. And we finally need our last entry, which is second row, second column. So it's going to take second row, second column. So that's going to give me 4, 5, 6 dotted with 2, 4, 6. So as you get more experienced, you won't be working through in all this gory detail, but I wanted to show you exactly what it looks like. So let's carry on working here. Okay, so we've got 1, 2, 3 dotted with 1, 3, 5, so that's 1 times 1, which is 1, plus 2 times 3, which is 6, and 3 times 5, which is 15. Next entry is 1, 2, 3 times 2, 4, 6. That's going to give us 1 times 2, which is 2, plus 2 times 4, which is 8, plus 3 times 6, which is 18. Now we've got 4, 5, 6 times 1, 3, 5. So that's going to give us a 4 plus a 15 plus a 30. And finally, we've got 4 times 2, which is 8, plus 20 plus 36. So we're almost there. So now we need to add up 1, 6, and 15. So that's going to give us 22. Let's keep our colors going. 2, 8, and 18 is going to give us 28, 45, 49. And finally, we've got 28 plus 36, 64, I think. Yeah. Might have to check that last one. I'm really bad at addition. Just check that. Phew. Okay, so it is a bit weird and a bit cumbersome, but it is a definition that is super useful. So I'm not going to work through all of these examples. There are just a couple of key ones that I want to have a look at. So if we have a look at, so I'll put the final solutions in the final version, but you should work through them. So the first thing, so here, check, we've got a 3 by 2 and a 2 by 3. So notice I've switched the order in which I multiplied in my first example, and now I end up with a 3 by 3. Okay, let me just put a line here so that we don't think that that's an equal there. So this might be the first time that you'll realize that the order in which you multiply matrices is super important. So it's not like multiplying normal numbers where you can multiply in any order. The order really matters because you're going to end up with a matrix of a completely different size, depending on which order. So if you were to work out, so here we've got a 2 by 2 times a 2 by 2, so we're going to end up with a 2 by 2. And if you do this multiplication, you will find that you end up 1, 2, 3, 4. You get the same matrix back. So this is our first hint that matrices that look kind of like this, so with 1s down the diagonal and 0s everywhere else, act kind of like 1 in terms of multiplication. A couple more examples to look at. Here we've got 1 by 3, and here we've got a 3 by 2. So that's going to end up giving us a 1 by 2. So that we can certainly do, so that's fine. But if we switch the order, so now we've got a 3 by 2, and we're trying to multiply it by a 1 by 3, we can't do it. So you might have a situation where you simply cannot multiply two matrices together, or you might have a situation where you can multiply them in one order, but not any other order. Another key thing to note, if you are doing matrix multiplication with vectors, if you have a row vector times a column vector, so here we've got a 1 by 3 and we're multiplying it by a 3 by 1, that's going to give us the dot product. So this is giving us 1 by 1, so this is our dot product. But if you switch the order, so here I've got 3 by 1, and I'm multiplying it by a 1 by 3, now suddenly you're getting a 3 by 3 matrix. So again, order is super important. And you can have a look at the two examples that I give there. I think for both of them, you can't multiply at all. So this is just emphasizing some of the weirdnesses about matrix multiplication. So just summarizing that, it's not possible to multiply every two matrices, and matrix multiplication is not commutative. So this means you have to be careful about the order. It's not the case that A times B is equal to B times A. And in fact, it might be that AB is defined, but BA isn't. And the other thing that is a bit strange, we're used to when we multiply two numbers together, we get another number. But when we multiply matrices together, you probably, unless the dimensions of the input matrices are very specific, what you get is going to be a matrix that has its own dimensions. So yeah, it's all a bit strange. Why do we care? Why are we doing this? Well, the first reason that we're doing this is because it's going to give us a way of working with systems of linear equations that is very generalizable and super computable. So what we do is we take, for example, this system of linear equations, and we're going to turn that into what's called a matrix equation. So we're going to define, I'm going to define a matrix A, which I will call a coefficient matrix. And this is going to be the coefficient. So each row of my matrix is going to look at a specific equation, and it's going to just take the coefficients for each of the variables. So here I would have a 1. Now x2 isn't showing up. That means it has a coefficient of 0. And then I have a -1. If I look, oh, and I see I've actually got 4 variables. So I should have this over here, and x4 is also a 0. Okay. Looking at our second equation, that's going to give me my second line. That's going to be a 4 and a 0 and a 0 and a -2. And if I look at my third equation, that's going to give me a 0, a 2, and a -2, and a -1. Okay. And now I'm going to define a matrix. Okay, and the thing to note here is that this is a 3 by 4 matrix. I'm going to define a vector which is going to be x1, x2, x3, and x4. And finally, now I can write my matrix equation very neatly, which it looks like this. which is pretty cool. So here I am using the convention that I just know what the dimensions of that zero vector should be. And in fact, we can see from our original equation over here that our zero vector is going to be equal to 0, 0, 0. And here I am using matrix multiplication. So just to convince you, if I multiply out my crazy matrix A by x1, x2, x3, and x4, what do I get? Well, I know that it's going to be a 3 by 4 times a 4 by 1, so that's going to give me a 3 by 1. My first entry is going to be 1 times x1, 0 times x2, minus 1 times x3. My second row is going to be 4 times x2, 4 times x1 plus 2 times x4. Did I get that right? Yes. And my final entry is going to be 2x2 minus 2x3 minus x4. And I know from my equation that this needs to be equal to 0, 0, 0. And now you can see that within my matrix equation, I have my system of linear equations because this entry has to equal this. That is my first equation over there, and so on. So my second equation is given by matching those entries, and my third equation is given by matching those entries. Okay, so that was quite a lot. What do you need to know from this lecture? You need to know what a matrix is and the notation that we use to describe them. You need to be able to check if two matrices are equal. So remember, it's dimension and corresponding entries. You need to be able to add and subtract, multiply by a scalar. You need to be able to find the dot product because you need that in order to be able to multiply two matrices. And the final thing is you need to know how to convert a system of linear equations into matrix format and vice versa. Okay, so I haven't really shown you why the matrix format is useful. We'll do that in the next lecture. Right. See you in a bit.